Hi everybody. So in this video I'm going to show you how to find the scalar product equation of a plane and then to use this to find the Cartesian equation of a plane. And we're going to use this property which I showed you in a previous video, and I'll come back to this later. So in this plane we have a position vector we call A, and this originates from the origin. We have R, which is a general position on this plane, so R can be anywhere on this plane. For this example I've put it here. And then we have a normal vector which passes through the plane at 90 degrees. It's really important that this is perpendicular to the plane. So to find the scalar product equation of this plane, we need to begin by finding the difference between our general point and our known position vector. So we need to be able to go from A to R. And to do this, we can go from A to the origin, and then from the origin to R. So this will be negative A plus R, or R minus A. And this vector runs along the plane, which means it must be perpendicular to this normal vector. If we were to move it up here, you can see that this would be 90 degrees between the normal vector and R minus A. So now if we consider each of these two vectors and substitute them into our scalar product equation, then we can say that A is our normal vector n, and B is our vector R minus A. So we get n dotted with R minus A will equal the magnitude of n multiplied by the magnitude of R minus A and the cos of theta. But we know this theta is 90 degrees because R minus A must be perpendicular to this normal vector. And the cos of 90 is 0, so this entire right-hand side will become 0. So n, when dotted with R minus A, will equal 0. Then we can expand out this bracket. So n dotted with R is equal to n dotted with A. And when you dot two known vectors together, we get a constant, which is the scalar. And we'll call this constant d. And this is the scalar product equation of a plane, where you have a perpendicular vector to the plane, dotted with the general position vector of that plane, will equal some constant d. Okay? In our next example, we're going to use this relationship to find the Cartesian equation of a plane. Okay, so now we're going to find the Cartesian equation of this plane. We have our normal vector, we have our position vector on the plane, and we have a general vector r. This n could be a general vector with the x, y, and z components a, b, and c. And this r would be a random point on the plane with an x, y, and a z coordinate. So we have our two vectors, n and r, and we can substitute them into this scalar product equation. So we have r dotted with n, and this will equal a constant d. Now we can dot these two together, so we'll have x times a plus b times y plus c times z, and this will equal the constant d. And this is the Cartesian equation of a plane. In our next examples, we're going to look at how to find the scalar product equation and the Cartesian equation of a plane when we're given a fixed position vector. Okay? Okay, so in this question, we're told that point Q lies on a plane pi with this position vector and this vector which is perpendicular to the plane, and this is our normal. We've been asked to find the scalar product equation of this plane. So the first thing I'm going to do is I'm going to sketch a diagram. So we have our position vector, which I've labeled point A. We have our normal vector, which we've called n, and our general position vector r. and we're going to use the scalar product equation given here. So we'll say that r, when dotted with n, will give us a constant d, and we need to find this constant. So now we can substitute this position vector in place of r, and when we dot these two together, we get 3 times 2 plus negative 2 times 5 plus 4 times negative 1, which gives us a constant of negative 8. So the scalar product equation will be r dotted with n will equal negative 8. And this is the scalar product equation of this plane. Okay, let's try one more example. Okay, so finally, we're told that point P lies on the plane pi with these coordinates, and this vector is perpendicular to the plane. We've been asked to find the Cartesian equation. So perhaps you want to try this question yourself. You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back to You Ready to Go. So the first thing I'm going to do is I'm going to sketch the diagram. So we have a position vector of point P, a normal vector, and a general point R for our plane. So to find the Cartesian equation, we need to use this relationship, where the A would be the 2, the B would be the negative 5, and the C would be the negative 8. So I can substitute each of these into this equation. And then we can find the constant D using this position vector, where the 8 is the x, the negative 3 is the y, and the 6 is the z value. So I've substituted these into the equation. We can work out this left-hand side. So we get the 16 plus the 15 minus the 48 will give us a constant value of negative 17. Then we can substitute this value of d back into our equation here. So this is the equation of a plane. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and worksheet from my website, mrmathematics.com. I'll leave a link in the description below.